r multiplied by r, so r squared, you integrate that, so it will be r cubed over 3 from 0 to 4, and then d theta here, like this. After that, we can, so 0 pi over 2 cosine theta, and then when you substitute, you get 64 over 3 d theta, so 64 over 3 integral from 0 to pi over 2 of cosine theta. The integral of cosine, of course, is sine theta, from 0 to pi over 2, and you substitute and you will get 64 over 3 as the final answer in this integral. It's fairly simple to do this way. So by using polar coordinates, we are able to evaluate this integral without too many problems. So replace x with r cosine theta, y with r sine theta, and then the rest is fairly easy to do. Well, in spherical coordinates, that's what we do. What we do here, rectangular coordinates x, y, z, you take two of these coordinates, x and y, and you replace them with r and theta. And you keep the z as it is. Z stays as z. So we take two of the three coordinates and we replace them with polar coordinates. So here it's x and y, which are replaced by their polar coordinates r and theta. So you have a point r theta z. Z is the same, and then instead of working with x and y, we work with r and theta. So that these three coordinates, theta, r, and z, are what we call the cylindrical coordinates. Okay, so that is the idea of cylindrical coordinates. R, theta, and z. Okay, write the equation of the cylinder. This is this cylinder here. Its equation is x squared plus y squared equal to 16. If we want to write its equation in cylindrical coordinates, then x squared plus y squared is r squared equal to 16. So that will give us r equal to 4. That is basically the equation of this cylinder in cylindrical coordinates. So r is equal to 4. Here, this time we have a cone, z squared equal to x squared plus y squared. It's this cone that you see here. And I want to write this equation using cylindrical coordinates. So z stays the same. So it will be z squared. And x squared plus y squared is r squared. Yeah, like this. So it will be z squared equal to r squared. We can keep it like this. Or that means z is equal to r. Or maybe z is minus r. Yeah, this is a bit like when you have x squared equal to 4, then x may be 2 or maybe minus 2, like this. Yeah, same thing. Now you are getting two equations. This half of the cone is where z is equal to r. It's a positive value. And this half of the cone is where z is minus r. Z here is a negative number. It's below the xy plane. So you get the full cone described by these two equations. Okay, no problem. This one, if you want to write this equation in cylindrical coordinates, then the z stays z, and x squared plus y squared again is r squared. Yeah, so this equation is the same as this in cylindrical coordinates. This is using x, y, and z. This is using r, theta, and z, like the cylindrical coordinates, like this. So I think no huge problems here. So I repeat, cylindrical coordinates are a situation where you replace two variables with the polar coordinates r and theta. Here we're talking about x and y, but sometimes we may replace y and z with the polar coordinates. It just depends on what we want to do with these cylindrical coordinates. Okay, so that is the example on polar coordinates, r and theta. Okay, now when you integrate triple integral using these cylindrical coordinates, basically what you do is you z, keep the dz, but dx, you replace it with r, dr, d theta. Yeah. So basically, dv, when you see the dv, it will be dz and then r, dr, d theta, like this. So dx, dy, dz should be replaced with r, dz, dr, d theta that you can see here at the end. So let's see what we can do there in this example. I want to write this integral as a triple iterated integral in cylindrical coordinates if Q is this solid here. Q is the solid between Z equal which is Z equal R. This is the cone. And the other side you have Z equal square root of 18 minus x squared minus y squared. When you square both sides, you get z squared equal to 18 minus x squared minus y squared. So that will give us z equal, or no, I will not, maybe I will not square. I will not square. No need for squaring. I will just write this as the square root of 18 minus r squared, like this. And this is the sphere that you can see here. So it's basically between these two solids. Their intersection is a circle. So you have a solid like this. Okay. Now, I want to find their intersection. If you put the intersection of these two solids, you will see r equal square root of 18 minus r squared, and then you square both sides. So we get 2r squared equal to 18. So r squared equal to 9, which will give us r equal to 3. That means this intersection between them is a circle of radius 3. So if you project it like this, it's a circle of radius 3, which is here. So now, if I want to write the integral of any function r theta z, yeah, dv, in this solid Q, I will have to integrate with respect to z first, fr theta z dz from this bottom surface into the top surface. So from square root of 18 minus r squared to, oh, sorry, no, this is, the bottom is the cube, is actually the cube, yeah. So it's from the cube, from the cone, yeah, from z equal r to the top, which is the square root of 18 minus r squared dz, and then I will integrate r dr d theta. This is in the circle of radius 3, so from 0 to 3, and from 0 to 2 pi, like this. So that is the way. So we integrate with respect to z from the cone to the sphere. So cone, sphere, and then we integrate in this circle of radius 3, which is r from 0 to 3, theta from 0 to 2 pi, like this. Basically, that's how we can integrate this. So first with respect to z, vertically, and then in the region R using polar coordinates. All right, now we have another example here where we want to integrate, okay, with respect to z from here to here. So that's fairly easy to do. Yeah, let me just so z from x squared, and I change this into z equal r squared. So this will be an r squared. The top one, 2 minus x squared minus y squared, will give us z equal 2 minus r squared. So these are the boundaries for z, this and this. Then the y goes from minus to y equal square root of 1 minus x squared. This is telling us, and x, yeah, finally, x is between minus 1 and 1. These all of this is telling us that x and y are in a circle of radius 1. Like this. This half a circle is y equal minus, like that, and the top half is y equal square root of 1 minus x squared. So y goes from here to there, and x goes from minus 1 to 1. So that means this is a circle of radius 1. Okay, and that means r will go from 0 to 1 and theta from 0 to 2 pi. Okay, now we have everything we need. So that means our integral I can now write the integral as x squared plus y squared, which is basically r squared to the power of 3 over 2 dz, and then r dr d theta, where r, this goes from r squared to 2 minus r squared. Small r goes from 0 to 1, and theta from 0 to 2 pi, like this. Okay, after this, we integrate. We're going to integrate. So let me leave 0 to 2 pi, 0 to 1, and then integrate this. When you multiply, it's going to give us r3, okay? Multiply by this r, so it's actually a total of r to the power of 4, actually. So I will put r to the power of 4. Yeah. Dz, and actually when we integrate the dz, I just get z, so let me put z here, no problem. So I will put z from z equal r squared to 2 minus r squared. And then I will have dr and d theta like this. Okay, so 0 to pi, 0 to 1, r to the power of 4, and then we substitute. We will have 2 minus r squared and another minus r squared when we substitute here dr d theta, like this. Okay, now we need to open this bracket, 0 to pi, and when we open that, okay, these two will give us minus 2r squared. So it's going to give us 0, 1, 2r power 4 minus 2r to the power of 6 dr d theta. It's a long thing. So integrate this will give us 2 over 5 r to the power of 5. And we integrate this 2 over 7 r to the power of 7 from 0 to 1 d theta. And finally, we will get this. When you substitute this, I will get 4 over 35, and then the integral from 0 to 2 pi d theta, which will be 2 pi. So in the end, 8 pi over 35 is the final answer. A really long process here. It goes, let me just go through it again and see what happens. You can see that dz, z goes from this to this. So I write these two equations. I change them into these polar coordinates, r and theta. So they become z equal r squared and z equal 2 minus r squared. And then the y goes from this curve to this curve, but these are actually half circles. They're all part of the circle, because if you, this you can change. If you square both sides, you will get x squared plus y squared equal to 1, where y is a negative number. So it's the bottom half. And this one, x squared plus y squared equal to 1, where y is a positive number, so it's the upper half. So basically y goes from here to here. And x from -1 to 1, that means we are covering the whole circle of radius 1. That means r goes from 0 to 1, theta from 0 to 2 pi, and then we just move into the cylindrical coordinates dz, r, dr, d theta, like this. And we do the calculation. Okay. Not an easy one, but that's how things are. Here, we're going to use triple integral to find the volume of the solid bounded by this paraboloid, which is in blue here, and the xy plane, that means this here. So we want to find the solid, the volume of this solid. Okay. This time, what we're going to do is we will keep y as it is. We will not change anything in y. But we will change x and z into r cosine theta and y equal, sorry, z. Yeah. Yeah. I will put z equal to r sine theta, like this. And you can see from the graph that y will go from this point here where y is 0, so it's on the xz plane, to this one where y is 4 minus r squared. So y from 0 to 4 minus r squared. So we're integrating in this direction here. And r, we need to find r, and we need to find the boundaries for theta. After that, we can integrate using this cylindrical coordinates. Now, to find r and theta, the boundaries, we need to look at this circle here. this is where y is equal to 0. So put y equals 0 in the equation. X squared minus z squared. So we get x squared plus z squared equal to 4. So it's a circle of r equal to 2. So it's a circle of radius 2. So r from 0 to 2. And because it's the full circle, we go from 0 to 2 pi like this. Okay. So now we can write the volume of this solid is the triple integral over q dv. So now let's move to the cylindrical coordinates. So it's going to be the integral with respect to y from 0 to 4 minus r squared, and then r dr d theta. R from 0 to 2, and theta from 0 to 2 pi, like this. So the rest is really not that difficult. So the integral with respect to y first, so that will give us y from 0 to 4 minus r squared, r dr d theta. So 0 to pi, 0 to, substitute, we get, and this r here, I will write it, beginning, and 4 minus r squared dr d theta, like this. Now we can integrate. So multiply and integrate. So it's going to give us 2r squared. And then multiply will give us r to the power of 3. So minus r 4 over 4 from 0 to 2. And then d theta, like this. And then we substitute. If we substitute, I think we get 2, 0 to 2 pi. We get 4. 4. And then d theta. So it's 4 times 2 pi, and the answer is 8 pi is the volume of this solid. So again, let me repeat this. So you have this solid. The equation is given here, and we want to find its volume. So we will find the volume by integrating with respect to y from y equals 0 to y equal 4 minus r squared. And then so first with respect to y, and then with respect to x and z, we move those into polar coordinates. So in the end, we get these cylindrical coordinates y, r, and theta, and we can use them to find the volume here. Yeah, so it's all explained here. So from 0 to this, and then you have the circle. Okay. Okay, so that is basically this. Let me just go through some examples just to see how it works. Now, so we want to change these equations into cylindrical coordinates. So suppose you want to change this equation into cylindrical coordinates, what will it be? What is x squared plus y squared? R squared, yeah, good. R squared equals 16. Or you can change this into R equal, yeah, 4. That's it. So that is, and if you want to graph this, by the way, you want to graph this equation, it's x squared equal x, y. So it's a circle of radius 4, and then it goes all the way up and up like this. So this is basically the graph of this equation. It's a cylinder of radius 4. Now, this one, if we want to change it into cylindrical coordinates, how can we do that? Okay, let me just take a screenshot of the attendance, because I noticed now some are not bothering to turn up for these classes. So let me just, okay. So Mariam. Okay, thank you. Yeah, exactly. Now, what we're going to do is we can open the square, yeah? If we want, yes, we can open the square, so it becomes x squared minus 4x plus 4 plus y squared equal to 4. Okay, good. That's the first step. Then, now we, x squared plus y squared, I can replace that with x squared with r squared, yeah? R squared, yes. And then minus 4, remember x, yeah? X is r cosine theta. Yeah, exactly. So we can put here minus 4 times r cosine theta. And this 4 and this 4, by the way, will give you 0. Yep. So the 4 and the 4 will cancel. So we get this equation. We can leave it like this, or we can simplify it a bit if we want. You can, yeah, r squared equal to 4r cosine theta, and divide both sides by r, yeah, divide by r both sides, you will get r equal 4 cosine theta is perfectly okay to keep it like this. So any one of these will be fine. This one, any one of these equations is okay, no problem. This one, z equal x squared plus y squared, very easy, yeah. Z equal r squared, that's it. Yeah, good. Z equal r squared is fine. We can even do 7 if we want to. Yeah, so that will be, so if you want to do this 7, yeah, good. So I will write r sine theta equal to 2 times r cosine theta. You can simplify, you can divide by r, yeah, if you want. So it's going to be sine theta equal to 2 cosine theta. What happens if we divide by cosine both sides? Yeah, it becomes a tangent. So tangent theta is equal to 2. And I can even say then theta is tan minus 1 of 2 also is okay. This, all of these are fine. So That is basically the equation. All of these equations can be changed into cylindrical coordinates by using these techniques. Okay, good. All right, here yeah, I want to write a triple integral in cylindrical coordinates where Q is given by is the solid above z equal square root of x squared plus y squared and below this thing here. Yeah. Actually, what happens is we can graph. It's not necessary to graph. I think you can do it without graphing, but let me just. The first one, z equal this, is a cone like this. And the second is a sphere. Yeah, it's a sphere. Yeah, you can continue it like this. Yeah. So basically, so this is the solid Q that we are talking about. So the red graph is the cone. So Z equal, you can see that its equation is Z equal square root of R squared. So it's going to be R, so Z equal R. So we're integrating with respect to Z first from Z equal R to the top, which is this one, where Z yeah, is square root of 8 minus R squared. So this is surface number 2 here. Yeah. So we will integrate with respect to Z from Z equal R to Z equal square root of 8 minus R squared. And then we need to look at the R and theta. R and theta will be given by this circle where the intersection happens. So you need to look at the intersection between Z equal R and Z equal square root of 8 minus R squared. So then you square both sides and you move minus R squared to this side. So you get R squared equal to 4. So R is equal to 2. And that's it. So we now have everything we need. So the integral, then I can say that the integral of f of x, y, z dv in the solid Q can be found by integrating with respect to z. So f x, of course, is r cosine theta. The y will be r sine theta. The z will be just z. The dv will be dz, and then r dr d theta, like this. Now, z, what are the boundaries for z? What do I put here? What do I put here? Yeah, from R Yeah, good. So I will integrate z from z equal r to z equal square root of 8 minus r squared. Very good. So this is the integral with respect to z. After that, I will integrate with respect to r dr from what to what? 0 to 2. Great, thank you. 0 to 2. And finally, the theta, remember I'm integrating in the full circle. This is our r. So from 0 to 2 pi, like this. That's it. So that is basically the way we can integrate a function f given in this solid Q, which is, but the function is not given, so that's the answer. And we leave it there. We leave it there. Okay, let's try and see the same idea here. Q is the solid above the xy plane and below this paraboloid here. So basically, this time, Q is this solid, and its equation, yeah, z equal 9 minus x squared minus y squared. Okay, so that is the solid Q. So to integrate any function over Q, f of x, y, z dv, I could, yeah, integrate with respect to z from the bottom surface, which is z equals 0, to the top, which is z equal 9 minus r squared. Yeah. So I'm integrating in the z direction first, like this. And then I will integrate over the region R, which is a circle. Now, how do I get the radius of this circle? This is where z, what happens on the xy plane? Z is equal to 0. Yes. So you put z equals 0 in this equation, you will get 9 minus x squared minus y squared equal to 0. So x squared plus y squared is 9. So r squared is 9. That means r is 3. Yes, r is equal to 3. Okay, so that means I can now write the integral as this integral will be integrate f r cosine theta r sine theta z. Let me, yeah, and then dz. Okay, I think I will have to. All right. So dz r dr d theta. Z from 0. So first, with respect to z, from 0 to what? What is the boundary here for z? 9 minus r squared. Good, thank you. Thanks, Noria. And then with respect to r, after that, yeah, remember this circle, x squared plus y squared equal to 9. So r is equal to 3. Yeah. So from 0 to 3. And finally, because we are covering the full circle, so we need to integrate from 0, the theta, from 0 to 2 pi, like this. So that way we can evaluate any integral in this solid Q that we have here. Okay, so let me just try and do one more of this, question 15. Okay, here we have the same thing. Set up the triple integral, yeah, in cylindrical coordinates. Q this time is bounded by the solid y equal, this time notice it's y equals something, yeah, 4 minus x squared minus z squared. So it's going to be this paraboloid this time. Yeah. Okay. Going through the point 4 here. Yeah. X, Z, and Y like this. Now this time, what do you think the cylindrical coordinates will be? Which ones do we need to change into polar coordinates? What do we do with Y? Do we change it or we keep it? Yeah, X and Z will go into polar coordinates, exactly. So Y will be kept as it is, no problem. So we'll keep Y because you can see we will integrate from Y equals 0 to this, which is Y equal 4 minus R squared. So Y will be kept as it is. Okay, so X will be R cosine theta, Z will be R sine theta, and the Y will just be Y, no problem. We will not change it. Now, the boundaries, you can see now, Y will be integrated from 0 to what? Y will go from 0 to 4 minus R squared. Very good. R, we need to see what R is, yes? By making R will come from this circle here. Now, how do we find this circle? By putting Y equal 0, exactly. Thank you. Yes. So that means 4 minus x squared minus z squared will be 0. So x squared plus z squared equal to 4. That means r squared is 4. That means r is 2. So this is a circle of radius 2. So from 0 to 2. And theta, again, because it's a full circle, will just go from 0 to 2 pi. And once we have this, then we can say that our integral will be f of r cosine theta y, keep it as a y, and then the z needs to be changed into r sine theta, and then dy, and then r dr d theta, like this. Now, the integral with respect to y will be done from 0 to 4 minus r squared, and then small r will go from 0 to 2, and theta from 0 to 2 pi, and we have our integral. All right. Okay. Before I do a couple more examples, we'll just take a 5-minute break, and we'll come back to this. Okay, just 5 minutes, and we'll be back. Okay, guys. So let's do two more questions. I want to have a look at 25 and 26 here. This time we really want to evaluate an integral. Up to now, we just set up some integrals. We did not actually calculate them. Here, we're going to evaluate this integral. Yeah, set up and evaluate the integral. Okay, so I want to evaluate this integral where Q is the solid inside the cylinder, x squared plus y squared equal to 4, and between z equal 1 and z equal 2. So to understand a little bit this integral, we can see what this Q, this solid is. So we have a cylinder, x squared plus y squared equal to 4, which is, so imagine the circle here of radius 2, and then the cylinder is like this. And then we only consider going all the way up, down, etc. But we will only consider this cylinder from z equal 1 to z equal 2. So this is the solid Q from z equal 1, which is here, to z equal 2, which is here. So that is the solid Q in which we want to integrate our function. Okay, so if you look at the solid Q then, Z will go from, what are the boundaries for Z in this Q? From 1 to 2, yeah? So Z, we will keep it. It will go from 1 to 2. And then we will use polar coordinates for X and Y. So X, yeah, so that is a circle. For X and Y, we will have an R and we will have a theta. And you can see the circle, of course, here. Yeah, the circle will be r squared equal to 4. So r is equal to 2. So from 0 to 2 and 0 to 2 pi. And that is basically the whole, yeah, of the cylindrical coordinate. So now we can write our integral. So let me write the integral. So it's going to be the integral over q of e x squared plus y squared dv. I'm going to move everything into these cylindrical coordinates. So it's going to be e r squared dz, z, and then r dr d theta. R from 0 to 2 and theta from 0 to 2 pi, like this. So this is our integral. Now I can continue this calculation. It's fairly easy to calculate this. Now ER squared is a constant. It does not depend on Z, so I can 0 to pi. I will have 0 to 2 ER squared. What is the integral of the dz when I integrate dz? I will get z, thank you. Yeah, great. From 1 to 2, like this. And then I will keep r dr d theta like that. Then the substitution will give you 2 minus 1, which is 1. So it's okay. So it's 0 to 2 pi. And then we will have r 0 to 2 r e r squared. Yeah. dr and then d theta. Okay, great. Now, how do we integrate this with respect to r? Yep, exactly. So I can put 2 here and half. Very good. Okay. And then what I'm getting is the derivative of this. So it's fine. We can now say it's half the integral from 0 to 2 pi. And this will be ER squared from 0 to 2 multiplied by d theta. Great. After that, it's going to be half, and then e to the power of 4 minus e to the power of 0, which is 1, and then the integral of 0 to 2 pi d theta, which will give us 2 pi. So final answer of this integral is pi multiplied by, yeah. Okay. Yes, Salha. Uh, these two are? Yes. Can I just say that something here? That in general, if you have something like this, then it is e to the power of u. This is really, really important. This is a very important rule. So for example, if you have e to the power of x cubed, and you have here 3x squared, then what is the integral of this? Anyone? E x cubed, that's it. Like this. Yeah. It's the derivative, because when you take the derivative of this, the derivative of this will give you this. Because EU, when you differentiate it, you get U dash EU. So when you integrate this, you get this. Are we okay with this? Like that. Yeah. So that means, for example, if you have 3, like 4R3 ER4 dr, then what will be this integral? For example, what will be this integral? E, yeah, E R to the power of 4, like this. So forget this, huh? Because it's the derivative. So that's why we don't have the 2R is the derivative of this. So it's okay. All right, so that is the answer for this integral. I'm going to do the same idea for 26, except I think I will make this a bit simple. I don't want to go into integration by part and so on. So instead of the square root, I will remove the square root. Okay, I will not I will do it without the square root. You will see in a moment why we do that. Okay, now this time Q is the solid inside the cylinder, a bit like the same as before, except, but it's also outside another cylinder. Okay, so let's understand then what's happening here. So this time we have a cylinder of radius 2, but we also have another cylinder, so it's inside this one, but outside the cylinder of radius 1. So you have another cylinder of radius 1. So it's between these two cylinders. This is what Q is this time. So that is the Q. Okay, so it's inside the cylinder of radius 1, but outside a cylinder, inside cylinder of radius 2, but outside the cylinder of radius 1. Okay, so now I want to integrate z e x squared plus y squared dv in this Q, in this solid Q. Now, and Z goes from 0 to 3. So what are the boundaries then here? Z will go from, I'm going to use the cylindrical coordinates, Z, R, and theta. So Z goes from 0 to 3. R will go from not 0 to 1. Remember, it's between, from 1 to 2. Thank you, Sarah. Yes, from 1 to 2. Because we are integrating between the two cylinders. We have one cylinder and another cylinder. So we're integrating between these two cylinders inside. So it's going to, R will go from 1 to 2. And theta, what happens to theta? From where to where? From 0 to 2 pi, yes. Because we're going around, all the way around. So basically we're integrating in like a donut like this. So R will go from 1 to 2, but we are going all the way around. So that means, the theta goes from 0 to 2 pi. After that, it's okay. We can now try and integrate. So this integral will be, okay, 0 to 3 for z, 1 to 2 for r, 0 to 2 pi for theta. Z e r squared and then dz, okay, and then r dr d theta, like this. Okay, now we can integrate with respect to z first. What will we get? if we integrate with respect to z first, z squared over 2, so we will get 0 to 2 pi. Don't touch this. 1 to 2, we will not touch it. Then we will get z squared over 2 from 0 to 3. Yeah. And I will keep the rest. Er squared is there. R is there. dr and d theta like this. Are we okay with this? Yeah? Okay. After that, we substitute. We get 9 over 2, which is a constant. I can take it out of the integral. And we will have the integral from 0 to 2 pi, the integral from 1 to 2, r e r squared dr d theta. Let me continue down here. Now, what will happen to integrate this? Yep, again, the half, the famous half. So I will put 2 there, and I will put 1 over 2 here. Yeah. So in the end, I will have a 9 over 4 integral from 0 to 2 pi, then er squared from 1 to 2, and then d theta. And then we substitute. It's going to be e to the power of 4 minus e. Yeah, like that. Multiply by 2 pi. By the way, do you know where this 2 pi is coming from? Yes? Okay. It's integral. I often don't do it, but the integral from 0 to 2 pi d theta always equal to 2 pi. So I use this often and and after that we are done. But we can simplify if you want this 2 and the 4. So it's going to give us 9 pi e power 4 minus e, all of this divided by 2. So that will give us the answer to this integral without too many problems. Okay, so in general then, do you understand this concept of cylindrical coordinates? What do we do in these cylindrical coordinates? Yeah. So you want to integrate with respect to x, y, z. Then you can keep one of the variables. Maybe you can keep z and change the others into r and theta, like this. It just depends on the shape of the solid we have to integrate in. So that's the idea of this cylindrical coordinates. Let me check if we can do maybe one more, or we are okay with this. Okay, I think I'll take another perhaps 5 minutes to have a look at 29. 29. Okay, here we want to integrate the function z between this z and this z. Okay. This is a cone, by the way. This is a cone, and this is a sphere. Okay. It's a cone like this, and a sphere like this. So I want to integrate z in this solid. So integrating z in this solid, we can use spherical coordinates. The first equation is z equal r. So we integrate from r. I think we saw this solid a moment ago. And this one will be the square root of 4 minus r squared. Square root of 4 minus r squared. Z dz, and then r dr d theta. And to find the boundaries here, this is the circle, the intersection between the two surfaces. So we have square root of x squared. Yeah, let me maybe use, yeah, use z equal r and z equal square root of 4 minus r squared. So you make these two equal, and you will see you square both sides. So you'll get 2r squared equal to 4. So r squared is 2. So r equal to square root of 2. Okay. Yes. So r then will go from 0 to square root of 2. And theta will go from 0 to 2 pi like this. So that's how we do that. After that, it's quite simple. So we integrate with respect to z. So what will be the integral of the z with respect to z? Z squared over 2, yes? Z squared over 2 from r to square root of 4 minus r squared, and then r dr d theta. So let me just continue here. So 0, 2 pi, 0 square root of 2, and then you substitute. I can put the half here. If we substitute 4 minus r squared, and then minus r squared also, yeah, r dr d theta. After that, it's quite simple. You can multiply out the bracket, integrate with respect to r, and you can complete this without too many problems. Okay, we will stop here. Thank you very much for your attention, girls. Any questions at all? Anything you want to ask regarding tests? Anything? Any? Okay. I will put a practice test for your test number 3. If you have any question with, let me know, please. I will send you the solutions if you need them. Okay. Okay. Well, I will check. I will check if it is possible. I will do it. Absolutely no problem at all. I don't mind doing that. I will see. I will see with the department chair and Dr. Adama and see what he says, and I will let you know. Okay. Any other questions? Anything? Yes, Maria. No? Okay. Okay. Thank you then, girls, and have a nice day and take care.